November 5, 1941. Bureau of Ships, Washington, D.C. John Niedermair stared at a blank sheet of paper and a set of requirements that seemed to contradict each other. The British needed a ship that could cross oceans yet beach itself on shallow shores. It had to carry 30-ton Churchill tanks yet draw less than 4 feet of water forward. It had to be simple enough to mass-produce yet sophisticated enough to survive the North Atlantic. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within hours, Niedermair sketched what would become the most produced warship design in history. The landing ship tank, an awkward, flat-bottomed vessel that crew members would mockingly call large, slow target. But hidden within that rough sketch was a manufacturing revolution that would transform not just naval construction, but the entire course of the war. The destinies of two great empires, Winston Churchill would later write, seemed to be tied up in some goddamned things called LSTs. He had no idea how right he was. But the story of the LST isn't about naval architecture or military strategy. It's about a technical decision that terrified traditionalists, was implemented by workers who'd never built a ship before, and cut construction time so dramatically that it made the impossible merely difficult. This is the story of how welding replaced riveting and changed everything. The problem began at Dunkirk. Between May 26 and June 4, 1940, the British evacuated 338,000 soldiers from the beaches of France. They brought the men home. They left everything else behind. Thousands of vehicles, hundreds of tanks, and the bitter knowledge that you cannot reclaim a continent without the ability to put heavy equipment directly onto enemy beaches. Landing craft existed. The landing craft tank could carry 5 30-ton tanks, but LCTs were 117 feet long, with a draft too shallow for ocean crossings. They had to be carried to combat theatres on larger ships or built in sections and assembled on site. Neither solution scaled to the numbers the British needed. Churchill had actually conceived of tank landing vessels during the First World War. Nothing came of it then. But in 1940, watching his armies return from Dunkirk without their equipment, Churchill revived the concept with characteristic urgency. He wanted a ship, ocean-going, capable of crossing the Atlantic or Pacific under its own power. Large enough to carry 3 36-ton heavy tanks, shallow drafted enough to beach itself and discharge directly onto shore. The British tried. Between August and December 1941, they converted 3 Maracaibo tankers, Bachacero, Misoa, and Tasajera, small tankers designed for the shallow waters of Lake Maracaibo, Venezuela. The bows were cut off, bow doors and ramps installed. The interiors scooped out to accommodate vehicles. They could carry 22 25-ton tanks or 18 30-ton tanks or 33 3-ton vehicles, plus 210 troops. They worked. Barely. But Britain's shipyards were stretched to capacity-building destroyers and corvettes for the Battle of the Atlantic. There was no industrial capacity to produce hundreds of these specialized ships. In August 1941, President Franklin Roosevelt and Prime Minister Churchill met at Argentia, Newfoundland, the Atlantic Conference. Among the many strategic discussions was the landing ship problem. Britain had the design requirements, America had the industrial capacity. In November 1941, a British delegation arrived at the United States Navy's Bureau of Ships. This is where John Niedermair enters the story. Niedermair was technical director of preliminary ship design. Not a household name, not a naval hero celebrated in histories, just an engineer tasked with an impossible problem. The British requirements were clear. The ship had to be 328 feet long with a 50-foot beam. It needed to carry 2,100 tons of cargo. It required a 14-foot draft for ocean stability, but only 3 feet 9.5 inches forward draft for beaching. How do you build a ship that's simultaneously deep water and shallow water? Niedermair's solution was elegantly simple: ballast tanks. Massive ballast tanks that could be filled with seawater for ocean passage, providing the 14-foot draft needed for stability in heavy seas. Then pumped out for landing operations, raising the bow to allow beaching in less than 4 feet of water. An anchor and mechanical winch system would help pull the ship off the beach after unloading. The rough sketch went to Britain on November 5, 1941. The British Admiralty accepted it immediately. They requested 200 LSTs to be built under Lend-Lease. 1 month later, December 7th, Japan attacked Pearl Harbor. America entered the war. The LST program shifted from a British order to an American strategic priority. But designing a ship and building it are entirely different problems, particularly when you need not 200 ships but over 1,000, when you need them faster than ships have ever been built before, when your coastal shipyards are already at capacity building carriers, battleships, cruisers, and destroyers. The solution would require moving shipbuilding away from the coasts, into America's interior, to shipyards that had never existed, built by workers who had never welded a ship, using a construction method that naval tradition viewed with deep suspicion. Riveting was how ships were built. It had been how ships were built since iron replaced wood in the 1850s. A riveted joint used overlapping steel plates connected by metal rivets hammered into pre-drilled holes. The process was labor-intensive, time-consuming, and produced joints of proven reliability. Every major warship, every merchant, vessel, every ship that mattered had been riveted together. Riveting required skilled workers. Riveters worked in teams. One man, the heater, heated rivets in a forge until they glowed red. Another man, the catcher, caught the thrown rivet in a can or with tongs. The bucker-up held a heavy bucking bar against the rivet's tail, while the riveter hammered the head. The process created the distinctive sound of shipyards, the rhythmic thunder of pneumatic hammers, thousands of rivets, hundreds of thousands, millions. One Liberty ship, a cargo vessel smaller and simpler than an LST, required approximately 1 million rivets. Each rivet hole had to be drilled, each rivet heated and driven, each joint inspected. The process consumed 1/3 of total labor costs. Welding was different, faster, potentially stronger, but controversial. Electric arc welding had existed since the 1890s, but shipbuilders were conservative. Welding produced joints that looked weaker. You couldn't see the fasteners, you couldn't count them. You couldn't inspect each one individually the way you could with rivets. Early welds failed, cracks propagated, ships split. In 1930, the New York Navy Yard developed stud welding to attach wood to steel. Through the 1930s, welding gradually proved itself in stationary structures, bridges, storage tanks, but moving a welded structure through ocean waves was different. The stress was dynamic, the consequences of failure catastrophic. The United States Maritime Commission, formed in 1936, took the risk. Their standardized cargo ships would be welded. The decision was driven by economics and speed. Welding required less steel because it didn't need overlapping plates. It required fewer workers because one welder could do the work of a riveting gang. It was faster because you didn't drill holes or heat rivets. The first ocean-class ships, later called Liberty ships, incorporated extensive welding. Naval architecture firm Gibbs and Cox modified the British design, specifically changing from riveting to welding for American shipyards. The Maritime Commission drove costs down and encouraged mass production techniques. This was the environment into which the LST entered, a moment when welding was being proven but not yet fully trusted, when the scale of war production demanded speed that traditional methods couldn't provide, when the choice between conservative tradition and innovative risk would determine whether enough ships could be built in time. The LST would be welded, completely welded, in shipyards that didn't yet exist, in locations chosen not for their proximity to oceans but for their access to steel and their solid bedrock foundations. The first LST keel was laid June 10, 1942, at Newport News, Virginia. By October, the first standardized LSTs were floated from their building docks. 23 were commissioned by year's end. Construction time for these early ships ranged from 4 to 5 months from keel laying to commissioning. This was already faster than traditional riveted construction, but it wasn't fast enough. The need was desperate. Churchill's complaint about destinies tied up in LSTs wasn't rhetorical flourish. It was strategic reality. At the November 1943 Cairo and Tehran conferences, Allied strategy was constrained by landing craft shortages. Amphibious operations in Europe and the Pacific competed for the same limited pool of LSTs. The invasion of Normandy was delayed not because troops weren't ready, but because there weren't enough landing ships. Donald Nelson, chairman of the United States War Production Board, visited London in September 1943. He called LSTs and LCTs the most important single instrument of war from the European theatre's viewpoint. He cabled that requirements had been grossly understated. Fewer than 300 LSTs existed in November 1943. The solution was already taking shape in America's heartland, in places that seemed absurdly wrong for shipbuilding. In cornfields along the Illinois and Ohio rivers, in locations chosen not for tradition but for the revolution that welding made possible. Seneca, Illinois. Population 1,235 in 1942. A small town on the Illinois River, 100 miles southwest of Chicago, surrounded by cornfields and prairie, about as far from any ocean as you could get in America. In May 1942, the Chicago Bridge and Iron Company began preparing a shipyard on 200 acres of pasture and corn land on the north bank of the Illinois River. Chicago Bridge and Iron's primary business was building pressurized tanks, water towers, storage tanks, structures that required precision welding. They had a reputation for quality workmanship and efficiency, particularly in welding. That reputation, and their location near America's steel-producing heartland, made them ideal for the LST program. But why build ocean-going warships in Illinois? Why launch them into a river 100 miles from the nearest Great Lake, 1,000 miles from the nearest ocean? The answer reveals the welding revolution's full impact. LSTs could be built in sections, prefabricated sections, welded together. This was impossible with riveting because drilled holes had to align perfectly across separate plates. But welded sections could be manufactured wherever steel was available, transported to assembly sites, and welded together rapidly. The flat-bottomed LST design allowed construction along inland waterways near steel fabrication yards. Empty hulls could be built far from coasts, then completed during the journey to deep water. The shallow draft meant LSTs could navigate rivers that conventional warships couldn't enter. Seneca was chosen because removing 30 inches of topsoil and creviced limestone revealed solid sandstone bedrock capable of supporting the weight of steel supplies and erected hulls. The 200-acre site was wedge-shaped with 3/4 of a mile along the river. 15 berths were arranged parallel to the river for erecting ships. Each LST was 327 feet long and weighed 5,500 tons. Sections were fabricated and hoisted into place, welded together. Very little scaffolding was used because scaffolding cost time and money. Speed was essential. Teams moved from ship to ship doing identical work on each one. The first LST at Seneca took 6 months to complete because the shipyard was being constructed simultaneously. The keel was laid in June 1942. The ship launched December 13, 1942. 880,000 man-hours to construct. By the time the last ship was launched, only 280,000 person-hours were required. The work had been cut by 2/3. Chicago Bridge and Iron planned to build 1 LST per week when peak efficiency was reached. They achieved 7 ships per month, 157 LSTs built before war's end, 39 gallons of champagne used to christen them. This was the pattern repeated across America's interior. 5 cornfield shipyards built 670 LSTs during the war. Missouri Valley Bridge and Iron Company in Evansville, Indiana, built 171 LSTs, the most of any shipyard. American Bridge Company in Ambridge, Pennsylvania, built 119. Dravo Corporation on Neville Island, Pittsburgh, pioneered prefabrication techniques. Jeffersonville Boat and Machine Company in Jeffersonville, Indiana, completed its allocation. These inland yards had advantages beyond proximity to steel. They had workforce availability. They could recruit from agricultural and industrial communities not already depleted by military recruitment. They could train workers rapidly because welding was simpler to learn than riveting. Most jobs at Seneca began with a 2-week training period. Welders trained for 4 to 6 weeks. That was it. 6 weeks to transform someone who'd never seen a ship into someone building ocean-going warships. This was only possible because welding was more learnable than riveting. One person with a welding torch could do work that required coordinated 4-person riveting teams. The skill ceiling was lower, the training faster, the scaling easier. Women entered these shipyards in unprecedented numbers. Dravo and American Bridge created all-women welding crews. By 1945, women constituted 25% of workers employed in durable goods production, up from 8% in 1940. The Seneca shipyard's population grew from 1,235 to 6,600 in 2 years. An industrial boomtown created almost overnight. The transformation from 4-month to 2-month construction time wasn't a single breakthrough. It was continuous process improvement enabled by welding's flexibility. Teams specialized. Some crews welded only hull sections. Others worked on bow doors. Others on the massive tank deck. As each crew repeated identical tasks on successive ships, they improved. Learned shortcuts, refined techniques, reduced wasted motion. The hull department welded 23,300 pieces, totaling 1,340 tons of steel per ship. Each weld had to be strong enough to survive ocean crossing and combat operations. Yet weak welds weren't discovered during construction. They were discovered when ships cracked, when stress fractures appeared, when vessels failed. This was welding's danger. This was why traditionalists feared it. A riveted joint might work loose, but you'd see it happening. A weld looked solid until suddenly it wasn't. The steel used in early war production had ductile to brittle transition, temperatures too high. In cold North Atlantic waters, steel transitioned to brittle state and ships could split. The SS Schenectady split completely in two while docked in calm waters in January 1943. 100 Liberty ships suffered serious stress cracks. Several broke apart. But the LST survived these problems better than expected. The brilliantly conceived structural arrangement provided unusual strength and buoyancy. Only 26 LSTs were lost to enemy action out of over 1,000 built. Only 13 to weather, reef, or accident. The welded construction proved more resilient than skeptics predicted. By mid-1943, construction time had dropped to 4 months. Operating experience led to design modifications. From LST 513 onward, the elevator transferring equipment between tank deck and main deck was replaced with a 12 by 32 foot hinged ramp. This ramp was more complicated but hastened disembarkation. Vehicles could be driven directly from main deck down to tank deck and across the bow ramp to the beach. By war's end, construction time had been cut to 2 months, from keel laying to commissioning. 2 months to build a 328-foot ocean-going warship capable of crossing oceans and beaching on enemy shores. Half the time it took in 1943. This acceleration wasn't just faster workers. It was the entire system optimizing around welding's possibilities. Prefabrication reached remarkable sophistication. At Pittsburgh's Dravo Corporation, prefabricated sections were manufactured at 5 area plants and brought together to the Neville Island yard for final assembly. Sections were welded rather than riveted, a job that eventually opened to thousands of women. As one vessel launched into the Ohio River, more were in production behind it. The challenge wasn't just building LSTs faster. It was teaching people who'd never welded anything to weld ships that would cross oceans carrying men into combat. May 1942. A young woman named Dorothy walked into the Chicago Bridge and Iron Training Facility in Seneca, Illinois. 3 weeks earlier, she'd been working in her family's general store. Now she stood before a welding instructor holding an electrode holder for the first time. The instructor demonstrated the technique. Strike the arc. Maintain consistent distance. Move at steady speed. Keep the weld pool molten but controlled. Dorothy practiced on flat plates, horizontal welds where gravity helped the molten metal flow smoothly. After 2 weeks, she progressed to vertical plates. After 4 weeks, to overhead welds where the electrode had to be held above her head, fighting gravity, preventing molten metal from dripping. After 6 weeks, she was welding hull sections for LST 215. This scene repeated thousands of times across America's shipyards. Agricultural workers became welders, shop clerks became welders, housewives became welders. The massive scale of production required massive workforce expansion, and welding made that expansion possible in ways riveting never could have. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. A riveting team required 4 skilled workers: the heater, who operated the forge and heated rivets to precise temperature; the catcher, who caught thrown red-hot rivets without dropping them or fumbling; the bucker-up, who held the heavy bucking bar perfectly steady against the rivet tail while absorbing tremendous hammer force; the riveter, who operated the pneumatic hammer with enough force to properly form the rivet head without cracking the surrounding plate. Each role required different skills developed through years of experience. You couldn't quickly train a riveting team because coordination mattered as much as individual skill. Timing had to be perfect. One person's mistake ruined the entire rivet, and ships required millions of rivets. Welding was different. One person, one torch, learnable in weeks rather than years. The skill ceiling was lower for basic competence, though mastery still took time. More importantly, welders could work independently. Production could be parallelized. Dozens of welders could work on different sections of the same ship simultaneously, without coordinating the way riveting teams had to. The numbers at Seneca illustrate the transformation. The first LST required 880,000 man-hours. The last required 280,000. That's not just workers becoming more efficient at the same task. That's the entire construction process being redesigned around welding's capabilities. Consider what 280,000 man-hours actually means. If workers labored 8-hour shifts, that's 35,000 shifts. If 200 workers were assigned to one ship, that's 175 days of continuous work, roughly 6 months. But Seneca was launching 7 ships per month by peak production. How? Ships overlapped. Multiple LSTs were under construction simultaneously at different berths. But more importantly, the work was front-loaded. Prefabrication meant hundreds of workers could manufacture sections in parallel before assembly began. Hull plates were cut and shaped, bow doors fabricated, tank deck sections prepared, superstructure components built, all simultaneously, all welded. When sections arrived at the assembly berth, they were already substantially complete. The assembly process became more like connecting large components than building from raw materials. 3 Caterpillar tractors moved completed sections to the launchway. Cranes hoisted sections, weighing tons into precise positions. Welders sealed the joints. This was only possible because welded joints didn't require pre-drilled holes that had to align perfectly across sections manufactured in different locations. Welders could accommodate small misalignments, fill gaps, adapt to reality rather than requiring perfection. Riveting demanded precision because holes either aligned or they didn't. Welding offered flexibility, but welding also demanded new skills and presented new challenges. A novice welder had neither the skill nor experience to match an old hand. Welding seams on flat deck plates with gravity helping the flow was simple enough. Overhead welding was much more difficult. One solution was positioning seams so welders could work in a downhand position, with electrodes held at waist level or below to avoid fatigue. That often meant bringing the workpiece to the worker. Large vertical parts to be welded were turned horizontal. Ceilings and overhead structures were welded inverted, then reversed when completed. Scaffolding was built to place welders in optimum positions. This required more planning than riveting, where teams could work in whatever position the ship's structure dictated. The quality of welds varied dramatically based on welder skill and conditions. A good weld was stronger than the surrounding metal. A bad weld was a fracture point waiting to fail. Unlike rivets, which could be visually inspected and tested individually, welds had to be X-rayed or tested destructively to verify internal quality. Non-destructive testing was primitive by later standards. Ships cracked. Liberty ships particularly suffered stress fractures. The SS Schenectady split completely in two at the dock in January 1943. The ship simply broke in half while moored in calm harbour waters. Investigation revealed the steel had ductile to brittle transition temperature too high. In cold water, the steel became brittle. Stress concentration at welded corners propagated cracks. The crack would race across a welded plate faster than it would in riveted construction because welded plates were continuous rather than interrupted by rivet holes. The solution wasn't abandoning welding, it was better metallurgy and design. Steel composition changed to provide higher fracture toughness, especially at lower temperatures. Ships incorporated crack arresters, belts of different steel high on the sides that would stop crack propagation. Design eliminated rectangular corners that created stress concentration points. New welding techniques reduced internal flaws. LSTs benefited from these improvements, but also from their inherently different structure. The massive tank deck was essentially a box beam, providing enormous structural strength. The flat bottom distributed stress differently than V-hulled cargo ships. The relatively shallow draft meant less stress from waves. LSTs proved remarkably durable despite early fears about welded construction. Throughout the war, LSTs demonstrated remarkable capacity to absorb punishment and survive. Despite the sobriquet large slow target, which crew members applied with dark humour, LSTs suffered few losses proportional to their numbers and operational scope. HMS LST 3002 was struck and holed in a post-war collision with a victory ship and survived. The brilliantly conceived structural arrangement provided unusual strength and buoyancy that exceeded expectations. The inland shipyards presented unique challenges beyond workforce training. Building ocean-going warships in cornfields hundreds of miles from salt water seemed absurd. Yet it worked because of Welding's flexibility and the LST's shallow draft. LSTs built at Seneca, Illinois, launched sideways into the Illinois River. The river was only 9 feet deep with narrow width. Traditional launching, where ships slide stern-first downways into water, wouldn't work. The LST would have grounded on the opposite bank or gotten stuck at an angle. Instead, Seneca's shipyard was arranged with berths parallel to the river. Ships were moved sideways to a central launchway, then pushed laterally into the water. They hit the water at 22 to 28 miles per hour, 5,500 tons of steel, sliding sideways into a river. The waves were substantial enough that spectators learned to stand well back, but the Illinois River channel was adequate for the shallow-drafted LSTs, even though they were 327 feet long. From Seneca, LSTs traveled down the Illinois River to the Mississippi River, then south to New Orleans for final fitting out and commissioning. The journey itself was part of the shakedown process. Coast Guard crews often trained Navy crews during this river cruise. By the time an LST reached New Orleans, the crew had basic competence in operating their unusual vessel. Pittsburgh's shipyards presented different challenges. Dravo Corporation on Neville Island and American Bridge Company in Ambridge were located on the Ohio River. Both had bridge-building experience and some barge construction background. But ocean-going warships were entirely new territory. Dravo had already launched a new type of subchaser, PC-490, for the United States Navy in October 1941. The first combat vessel built in Pittsburgh since the War of 1812, this earned Dravo the nation's first All-Navy E Award for production excellence in March 1942. The experience with PC-490 provided foundation for LST construction. American Bridge was a United States Steel subsidiary with extensive experience in structural steel work. Their reputation for quality and their location near steel-producing centers made them natural choices for LST construction. Between them, Dravo and American Bridge launched over 250 LSTs into the Ohio River between 1942 and 1945. The Ohio River presented advantages over the Illinois River: deeper channel, more width, better navigation. LSTs could travel from Pittsburgh down the Ohio to the Mississippi, then to New Orleans or direct to the Gulf of Mexico. The river system became an industrial highway, moving warships from heartland factories to coastal fitting-out yards. This wouldn't have been possible with riveted construction. Traditional shipbuilding required large coastal facilities with heavy equipment, extensive dry docks, and infrastructure developed over decades. Welding allowed shipbuilding to move inland because sections could be prefabricated anywhere. Steel was available, transported by rail or truck to riverside assembly sites, and welded together rapidly. Chicago Bridge and Iron's Birmingham, Alabama plant fabricated front sections for LSTs completed at Seneca, Illinois. These included the bow doors and ramps used to discharge tanks during beach invasions. Sections were manufactured in Birmingham, shipped by rail to Illinois, and welded into place. This geographic distribution of manufacturing was revolutionary. The workforce transformation extended beyond welding skills. Between 1940 and 1945, the number of female workers rose by 50%, from 12 million to 18 million. In durable goods production, women's representation increased from 8% to 25%. They operated machinery, streetcars, buses, cranes, and tractors. They unloaded freight, built dirigibles and gliders, worked in lumber mills and steel mills. But welding became particularly associated with women's war work. Rosie the Riveter, the iconic image created by Norman Rockwell and others, was actually an aircraft riveter. In shipyards, women weren't riveting. They were welding. Thousands of women welders worked in LST construction. Some shipyards created all-women welding crews who worked together as teams. The transition wasn't smooth. Trade unions objected strenuously to breaking complex shipbuilding jobs into smallest possible components and training workers to do specific tasks through repetition. Union leadership argued this practice devalued skilled labor and threatened journeyman workers who had spent years learning their trades. Management argued wartime necessity trumped union concerns. The conflict remained unresolved throughout the war, but the practical reality was undeniable. Years of training needed to make a journeyman shipyard worker couldn't be condensed into weeks. Yet the war wouldn't wait. Breaking shipbuilding into small components, training workers for specific tasks, and letting them gain experience through repetition was the only way to scale production to required levels. Welding made this approach possible because welding operations could be more easily standardized than riveting operations. Large and small classrooms sprang up in Bay Area shipyards and inland yards where welding and other crafts were taught. Despite resistance from professional shipbuilders, there was no suitable alternative. The ships had to be built, the workers had to be trained, welding provided the path forward. By 1943, construction time for an LST had been reduced to 4 months from keel laying to commissioning. This already represented remarkable improvement over traditional shipbuilding schedules. But operational experience led to continuous design modifications that further accelerated construction. The elevator system transferring equipment between tank deck and main deck was replaced with a hinged ramp, starting with LST 513 in mid-1943. The ramp was more complicated mechanically but allowed vehicles to be driven directly from main deck down to tank deck and across the bow ramp to the beach. This eliminated time-consuming elevator operations during landing operations. It also eliminated the elevator from the construction process, simplifying assembly. Armament increased as combat experience revealed vulnerability to air attack. Initial gun batteries were augmented until by 1945 the ultimate battery was 8 40mm and 12 20mm anti-aircraft guns. Additional weapons meant additional mounting points, additional welding, additional electrical systems. Yet construction time continued falling. By war's end, by early 1945, construction time had been cut to 2 months, 60 days from laying the keel to commissioning a fully operational ocean-going warship. This represented not just incremental improvement but fundamental transformation of shipbuilding through welding's capabilities. The first LST to see combat was LST 382, commissioned October 27, 1942, 133 days, from keel laying to commissioning. She reached the Pacific in March 1943. 7 months later, LSTs built at Seneca were being commissioned in 60 days. The acceleration wasn't just about welding technique, it was about what happens when an entire industrial system reorganizes itself around a new technology's possibilities. But speed came with a price that wasn't fully understood until men went to sea. December 1944. North Atlantic. LST 325 departed England as part of a convoy returning to the United States. She'd survived the invasion of Sicily, survived Salerno, where German fighter bombers wounded 4 crew members and 4 British soldiers, survived the beaches of Normandy on June 6, 1944, survived 9 months of supply runs across the English Channel. On December 28, crossing the North Atlantic in winter storms, LST 325 struck a large wave bow first. The impact was enormous. Steel screamed. The crew felt the ship shudder. When they inspected the damage, they found a large crack running across the main deck. The welded hull had fractured. Lieutenant Commander Mosier, the commanding officer, faced a crisis. They were in mid-ocean, no port within easy reach. Winter storms continued battering the ship. Every wave stressed the crack further. The engineering crew worked around the clock. Steel plates were cut to size. Welders worked in conditions that violated every safety protocol. Overhead welding in a rolling ship, salt spray interfering with arc stability, cold that made metal brittle and fingers numb. They welded patches over the damaged area. Emergency repairs at sea that would have been impossible with riveting. You cannot rivet hull plates in mid-ocean with a ship rolling in heavy seas, but you can weld if you're skilled enough and desperate enough. LST 325 limped back to the United States, arriving in Norfolk, Virginia, on May 31, 1945. She survived. Mosier received a Bronze Star for his leadership during the crisis. But the crack revealed the ongoing tension between speed of construction and structural integrity. This wasn't isolated. LSTs developed cracks. Liberty ships split in half. The SS John P. Gaines broke in 2 off Alaska in November 1943. The stern section remained afloat for 30 days before sinking, a testimony to the compartmentalization of welded construction, even in failure. The SS Schenectady split completely in half while docked in calm Portland, Oregon harbor in January 1943. One moment, a complete ship, the next, 2 separate pieces. These failures stemmed from multiple causes. Steel metallurgy with ductile to brittle transition temperatures too high, stress concentration at welded corners where rectangular openings created weak points, welding defects where improper technique left internal voids or inclusions, design flaws where load paths weren't properly considered. But they all shared one commonality. They happened in welded ships, built rapidly under wartime pressure by workers who'd learned their trade in weeks rather than years. The investigation following the Schenectady failure revealed uncomfortable truths. The steel used in early war production became brittle at temperatures common in North Atlantic winter. Welded construction allowed cracks to propagate, holes across continuous plates faster than in riveted construction where rivet holes interrupted crack paths. Poor welding technique created stress risers where cracks initiated. The combination was occasionally catastrophic, but the response wasn't to abandon welding. It was to improve everything around welding: better steel chemistry, higher fracture toughness, improved ductility at low temperatures, design changes eliminating rectangular corners in favor of rounded openings. Crack arresters, belts of different steel composition placed strategically to stop crack propagation. Better welding rod composition, improved technique training, more rigorous inspection. The question wasn't whether welding was inherently inferior to riveting. Properly executed welds were stronger than riveted joints. The American Welding Society had been founded in 1919 specifically to develop standards and improve practice. By the 1940s, welding science was well understood, but proper execution required skill, time, and quality control. 3 things in short supply when production schedules demanded 7 LSTs per month from a single shipyard. Welders at Seneca worked overlapping shifts: day shift, night shift, around-the-clock construction. The shipyard never slept. Arc flash illuminated the darkness. The distinctive crackling of welding torches created constant background noise. The same welder who'd been trained for 6 weeks was now working 10 or 12-hour shifts in winter cold or summer heat. Fatigue affected weld quality. Rushed work created defects. Inspectors couldn't X-ray every weld on a 328-foot ship. The trade-off was calculated at the highest levels. Ships might crack, some might fail catastrophically. Sailors might die from structural failure rather than enemy action. But the alternative was having too few ships to conduct amphibious operations at all. The mathematics were brutal but clear. More men would die from delayed operations than from occasional welding failures. Churchill's complaint about destinies tied up in LSTs wasn't hyperbole. It was strategic reality backed by operational research. At the November 1943 Cairo and Tehran conferences, Allied leaders debated Operation Overlord, the invasion of Normandy. American President Franklin Roosevelt, British Prime Minister Winston Churchill, and Soviet Premier Joseph Stalin met to coordinate strategy. The operation required thousands of landing craft. LSTs were the critical bottleneck. Fewer than 300 existed in November 1943. The shortage of landing craft, more particularly LSTs, threatened to limit Allied strategy throughout 1944. The apparent necessity of choosing between postponement of Overlord and abandonment of planned or proposed amphibious operations elsewhere was dictated by LST availability. Operations in the Mediterranean competed with preparations for Normandy. MacArthur's Pacific campaigns required LSTs simultaneously. Every strategic option depended on landing craft that didn't yet exist in sufficient numbers. Donald Nelson, chairman of the United States War Production Board, visited London in September 1943 and met with planners. He returned convinced that LST and LCT production was grossly understated relative to need. He called them the most important single instrument of war from the European theatre's viewpoint. His cables triggered production increases. Without the welding revolution, without the cornfield shipyards, without the ability to cut construction time from 4 months to 2 months, Operation Overlord would have been delayed beyond June 1944, perhaps into 1945. The strategic implications were enormous. Every month of delay meant more German fortifications along the Atlantic Wall, more concrete bunkers, more minefields, more obstacles on the beaches, more time for Field Marshal Erwin Rommel to strengthen defences. Every month of delay meant more time for Nazi Germany to develop advanced weapons. The V-2 rocket was already in production. Jet aircraft were entering service. Type 21 submarines with capabilities far beyond existing boats were under construction. More months of V-weapon attacks on London meant more civilian casualties, more terror, more destruction of British morale. And every month of delay meant more Holocaust victims. By November 1943, the final solution was in full operation. Auschwitz-Birkenau was operating at peak capacity. Every day of delay meant more trains arriving at death camps, more victims murdered. The strategic imperative to end the war as quickly as possible wasn't just military, it was moral. The welding revolution wasn't just about industrial efficiency, it was about compressing time itself. Buying strategic options through manufacturing speed, creating possibilities that didn't exist when construction took twice as long. June 6, 1944, D-Day, Normandy beaches. Dawn breaks over 5,000 ships, the largest amphibious invasion in history. LSTs weren't in the first wave. They were too valuable, too vulnerable, to risk in the initial assault where beach obstacles and enemy fire were densest. They remained offshore while smaller craft, Higgins boats and LCVPs, delivered troops to the beaches. But in the hours and days following the initial assault, LSTs became the workhorses of the logistics operation. As soon as beaches were secured, LSTs drove straight in. Bow doors opened, ramps dropped, Sherman tanks rolled directly onto French soil. Trucks followed, artillery pieces, ammunition, fuel, food, everything an army needs to fight. At least 53 Pennsylvania-made LSTs participated in the D-Day campaign. LST-1 earned 4 battle stars, including for landings at Salerno, Anzio, and Normandy. LST-47 and LST-49, both built at Dravo, appear in the famous photograph of Omaha Beach taken June 15, 1944. The photograph shows multiple LSTs beached on the sand, bow doors open, vehicles and supplies flowing ashore. It's one of the iconic images of D-Day aftermath. The industrial capacity that made those ships visible in that photograph, sitting in cornfields months earlier. On June 6 alone, LSTs brought 41,035 wounded soldiers back across the English Channel to hospital facilities in England. The tank deck that carried Shermans to France carried broken men home. 38 LSTs had been converted specifically to hospital ships with medical facilities, operating rooms, and recovery wards installed where tanks usually parked. Others served dual purposes, carrying cargo forward and casualties back, the ultimate utilitarian vessels. The American employment of LSTs enabled meeting offloading requirements after a storm destroyed the Mulberry Artificial Harbour at Omaha Beach on June 19, 1944. The Mulberry was an engineering marvel. Artificial harbours, constructed in England, towed across the Channel, assembled off the invasion beaches to provide sheltered water for cargo ships. When the storm destroyed the American Mulberry, logistics planners faced potential disaster. Without harbour facilities, how do you unload the tons of supplies an army requires daily? The answer was LSTs. The crude but functional ships that could beach themselves, that didn't need harbours or docks or cranes. They simply drove onto the beach, opened their doors, and offloaded. When the sophisticated artificial harbour failed, the primitive but reliable LST continued operations. Beach the ship at high tide, drop the ramp, offload vehicles, supplies, ammunition, food, fuel, wait for high tide, retract using the bow anchor and winch system, return to England for another load, repeat, thousands of times. This operational flexibility existed because welding enabled rapid construction. If LSTs took 8 months to build instead of 2 months, there wouldn't have been enough to cover harbour failures. If construction remained bottlenecked at coastal shipyards, simultaneous operations in Normandy and the Pacific couldn't have been sustained. The strategic flexibility that welding provided was as important as the ships themselves. In the Pacific, LSTs were equally critical but faced different challenges. The vast distances meant LSTs often made journeys of 67 days covering 9,800 miles from East Coast shipyards to combat zones. They crossed the Caribbean, transited the Panama Canal, crossed the Pacific, weeks at sea in a flat-bottomed vessel that rolled sickeningly in any weather. General Douglas MacArthur employed LSTs in his island-hopping campaigns and the invasion of the Philippines. His strategy of bypassing heavily defended islands and striking at weakly defended positions was only possible because LSTs provided logistical flexibility. You didn't need established ports, you just needed a beach with appropriate gradient. Admiral Chester Nimitz used LSTs at Tarawa, Saipan, Iwo Jima, and Okinawa. Each operation consumed dozens of LSTs. The Solomon Islands campaign, beginning June 1943, was the LST's combat debut. New Georgia, Rendova, Vangunu occupation in July 1943, Vela La Vela in August, Cape Torokina in November. Each operation refined LST tactics, learned what worked, what didn't, how to position ships for optimal unloading, how to protect against air attack, how to extract from beaches under fire. The commanding officer of LST 446 proclaimed after operations in the Solomons, "An LST is the only ship in the world of 4,000 tons or over that is continuously rammed onto and off coral, sand, and mud." This operational profile was unprecedented in naval history. Deliberately grounding a ship went against every naval tradition dating back centuries. Early LST operations required overcoming the 18th century language of the Articles for the government of the United States Navy. He who doth suffer his ships to founder on rocks and shoals shall be punished. Commanding officers worried legitimately about court-martial for deliberately beaching their vessels. The tension between operational necessity and naval regulation required explicit authorization from higher command. There were tense moments at Quonset, Rhode Island, in early 1943, when designer John Niedermair encouraged the commanding officer of the 1st United States LST to drive his ship onto the beach at full speed of 10 knots. The commanding officer hesitated. Everything in his training screamed against deliberately grounding a warship at full speed. Niedermair insisted. The design was proven in models and calculations, but theory and practice diverge. The commanding officer finally committed. Full speed ahead, the LST crashed onto the beach, the bow buried in sand. The structure held, the ballast pumped out, the ship sat stable, ready to unload. Everything about LST operations violated naval tradition, but necessity overrode tradition. The ships worked. They survived groundings that would have destroyed conventional vessels. The flat bottom distributed weight across broad area, rather than concentrating it on narrow keel. The structural box beam of the tank deck provided enormous strength. The ballast system allowed controlled beaching and extraction. The bow anchor and winch pulled ships off beaches when tide and engines weren't sufficient. By war's end, 1,051 LSTs had been built in American shipyards. 101 were cancelled in fall 1942 due to shifting construction priorities when initial orders proved excessive. 113 were transferred to Britain under Lend-Lease, 4 more to the Greek Navy. The Royal Navy operated LSTs in Mediterranean and European operations. Greek LSTs served in Aegean operations. Despite their large, slow target nickname, only 26 LSTs were lost due to enemy action out of 1,051 built. LST-333 was torpedoed and sunk by German U-boat off Algeria June 22, 1943. LST-313 was bombed and destroyed while unloading at Sicily July 10, 1943. LST-348 was sunk by German dive bombers at Salerno. Individual losses happened, but the survival rate was remarkable given the operational exposure. Only 13 LSTs were victims of weather, reef, or accident during the war. 6 LSTs were destroyed in a single ammunition explosion at Pearl Harbor May 21, 1944. LST-353 was moored when ammunition detonated. The explosion destroyed 6 ships and damaged many more, but this was the exception. Weather and operational accidents claimed relatively few ships considering the tens of thousands of beaching operations conducted under combat conditions. The survival rate vindicated both the design and the welded construction. The brilliantly conceived structural arrangement provided unusual strength and buoyancy that exceeded initial expectations. Welding, properly executed by adequately trained workers, produced ships that survived punishments that riveted vessels might not have withstood. The flexibility of welded construction actually provided advantages in damage control. Cracks could be patched at sea, damaged sections could be cut away and replaced, modifications could be welded in place without drilling new rivet holes. The legacy of the LST welding revolution extended far beyond World War II. It fundamentally changed shipbuilding worldwide. After the war, riveting disappeared almost completely from major ship construction. Welding became standard not because welding was proven, perfectly safe, but because the war proved it was sufficiently safe and undeniably faster and more economical. Post-war commercial shipbuilding adopted welding universally. Container ships, tankers, bulk carriers, all welded. The methods developed under wartime pressure became peacetime standard practice. The workforce trained to build LSTs carried those skills into post-war industries. The women welders who built warships became welders in automotive plants, construction, manufacturing. Some remained in shipbuilding, others applied welding skills in completely different industries. The social impact was profound. Women who'd worked in shipyards during the war had experienced economic independence and skilled labor. Many were pushed out of industrial jobs when men returned from military service, but the experience persisted. Women who'd welded LSTs knew they were capable of skilled technical work. That knowledge influenced the next generation. Daughters of women welders grew up knowing women could do that work. Chicago Bridge and Iron Company returned to building pressurized tanks and storage vessels after the war, but they applied lessons learned from LST construction, prefabrication techniques that allowed manufacturing components remotely and assembling on site, workforce training methods that emphasized rapid competence rather than traditional long apprenticeship. Quality control procedures developed under wartime pressure. The company that built 157 LSTs in Seneca, Illinois, became a global leader in large-scale fabrication and construction, eventually ranking 92nd among United States corporations in the value of World War II military production contracts. Dravo Corporation transitioned from LSTs to commercial barge construction and eventually offshore drilling platforms. The prefabrication methods pioneered for rapid LST assembly proved equally valuable for constructing massive oil rigs in sections that were assembled at sea. American Bridge Company continued structural steel work for bridges and buildings, incorporating welding techniques refined during wartime production. The Golden Gate Bridge had been riveted, post-war bridges were welded, the cornfield shipyards closed. Seneca's population declined from its wartime peak of 6,600 back toward pre-war levels, around 1,500. The 200-acre shipyard site returned to agricultural use. Corn grew where LSTs were assembled, but the industrial transformation persisted in less visible ways. Workers who'd learned welding didn't forget. Skills transferred to other industries. Communities that experienced wartime boom retained connections to broader industrial economy. The LST Memorial was established in Seneca in 2005, dedicating a monument to the shipyard and the 157 ships built there. Reunion events brought together former shipyard workers and LST crew members. The meetings were emotionally powerful. Welders met sailors who'd survived because of their work. Sailors thanked welders for ships that brought them home. The abstract connection between worker and product became concrete and personal. In 1986, crew members of LST-59 returned to Pittsburgh for their reunion. They chose Pittsburgh deliberately, the place where their ship had been made at Dravo's Neville Island yard, where young women had welded the hull that carried them across oceans into combat. The reunion was held June 6 through 8, 1986, commemorating the 42nd anniversary of D-Day. Many of the welders attended. Former enemies became friends. Former builders met former users. The ship itself had been scrapped decades earlier, sold for scrap in 1948. But the human connections persisted. LST-325, the ship that cracked crossing the North Atlantic in December 1944, survived. After emergency repairs in Norfolk, she was moved to New Orleans and fitted with a Brody system to launch light aircraft. She served in the Pacific but arrived after hostilities ended. After the war, she was transferred to Greece in 1964, where she served as Syros until 1999. For 35 years, she was a Greek naval vessel, completely refitted and modified. In 2000, a volunteer crew of American LST veterans, men in their 70s and 80s, sailed LST-325 across the Atlantic from Greece back to the United States. The journey took weeks. These elderly men operated the ship they'd served on 55 years earlier. The engines still worked, the hull still floated, the welded seams still held. She's now a museum ship in Evansville, Indiana, the city where Missouri Valley Bridge and Iron Company built 171 LSTs during the war. She's one of only 2 operational World War II LSTs remaining. The other is LST-393 in Muskegon, Michigan. Visitors can walk through LST-325 today, stand in the tank deck where 20 Sherman tanks once parked in 3 rows, climb to the bridge where officers navigated by dead reckoning across thousands of miles of ocean, touch the welded seams that hold the ship together 80 years after construction. The welds are visible. You can trace them with your fingers. See where separate plates joined to become a single hull. Feel the slight ridge where filler metal built up, the physical evidence of the welding revolution that changed warfare. Those welds represent more than metallurgical bonds. They represent the moment when American industrial capacity fully embraced mass production techniques. When necessity overrode tradition, when the speed required to win a global war forced innovation that permanently changed manufacturing, when workers trained in weeks performed work that traditionally required years of apprenticeship. John Niedermair's November 1941 sketch took hours to draw. It took 7 months to lay the first keel in June 1942. It took 133 days to commission the first LST in October 1942. By war's end in August 1945, that timeline had compressed to 60 days. 60 days from raw steel to ocean-going warship ready for combat operations. This acceleration wasn't just about working faster. It was about fundamental reimagining of what shipbuilding could be when organized around welding's capabilities rather than riveting's limitations. The LST's ugly, awkward appearance belied its revolutionary nature. Naval architects could design more elegant vessels. Engineers could propose more sophisticated systems with better seakeeping qualities and higher speeds. But the LST did what needed doing. It landed tanks on beaches. It crossed oceans despite flat bottom and shallow draft. It survived combat despite critics calling it large, slow target. And most importantly, it could be built fast enough, in large enough numbers, to change strategic calculations at the highest level of Allied planning. Winston Churchill never loved LSTs. His complaint about destinies tied to goddamned things called LSTs dripped with frustration, but he understood their necessity absolutely. Without LSTs in sufficient numbers, Operation Overlord couldn't proceed on schedule. Without Overlord, Nazi Germany couldn't be defeated through Western invasion. The Eastern Front would have borne even more weight. Soviet casualties would have been higher. The post-war political situation would have evolved differently. The strategic necessity was absolute and unquestionable. The welding revolution made LST production possible at required scale and speed. Riveting couldn't have scaled to 670 LSTs built at 5 inland shipyards, while coastal yards built larger warships. Traditional shipbuilding methods couldn't have compressed construction time from 4 months to 2 months, while maintaining adequate structural integrity. Coastal shipyards couldn't have handled the volume while simultaneously building carriers, battleships, cruisers, destroyers, and submarines. The answer was welding. Inland shipyards built from scratch, rapid workforce training that violated union traditions but met wartime necessity, prefabrication that allowed parallel manufacturing, mass production techniques applied to complex military hardware, industrial methods that traditionalists viewed with suspicion but necessity demanded. The ships cracked. Some failed catastrophically. Men died when welded hulls split in cold water. But more men would have died if too few ships existed to conduct amphibious operations when strategic windows opened. This is the uncomfortable mathematics of wartime production: quality versus quantity, safety versus speed, long-term reliability versus immediate necessity, perfect versus adequate. The LST program chose speed, chose quantity, chose getting adequate ships in sufficient numbers over waiting for perfect ships in insufficient numbers. The choice succeeded by every measure that mattered. 1,051 LSTs built. Operation Overlord launched June 6, 1944, on schedule. Pacific Island campaigns prosecuted simultaneously. Strategic flexibility maintained throughout 1944 and 1945. Allied victory achieved May 8, 1945, in Europe and August 15, 1945, in the Pacific. The cost in cracked hulls and occasional catastrophic failure was real: 26 combat losses, 13 operational losses. But it was far lower than the cost of defeat or even the cost of delayed victory. The LST stands as monument to American industrial capacity in its peak moment. The ability to design, prototype, refine, and mass-produce complex systems at unprecedented speed. The willingness to embrace new technologies when necessity demanded, regardless of tradition. The capacity to train workers rapidly and deploy them effectively despite union opposition. The industrial infrastructure that could build ocean-going warships in cornfields hundreds of miles from saltwater. These capabilities didn't emerge spontaneously. They resulted from deliberate choices made under extraordinary pressure, choosing welding over riveting, choosing inland shipyards over coastal bottlenecks, choosing rapid training over traditional apprenticeship, choosing prefabrication over on-site assembly from raw materials. Each choice involved trade-offs. Each trade-off was calculated against strategic necessity. Each calculation proved correct in the crucible of global war. The welding revolution that cut LST construction time from 4 months to 2 months represents one of World War II's critical but underappreciated innovations. More dramatic stories exist. Atomic bombs that ended the Pacific War, radar that won the Battle of Britain, code-breaking that revealed enemy intentions. But the humble LST, welded together in cornfields by workers trained in weeks, enabled operations those other innovations supported. Without LSTs, Allied armies couldn't land on enemy shores in sufficient strength. Without welding, LSTs couldn't be built in sufficient numbers fast enough. Without the cornfield shipyards, welding couldn't scale to required production rates. Without rapid workforce training, the shipyards couldn't staff adequately. The entire system had to work together. Every piece had to succeed. And remarkably, it did. The legacy persists in modern manufacturing. Welding techniques refined under wartime pressure, prefabrication methods developed for speed, workforce training approaches that prioritized rapid competence over traditional credentialing, post-war commercial shipping, offshore oil platforms, construction industries, automotive manufacturing, and countless other fields inherited these innovations. When you see a container ship, you're seeing welding perfected over decades since the LST proved it viable. When you see an offshore oil rig, you're seeing prefabrication refined from wartime necessity. When you see large-scale construction projects completed rapidly, you're seeing workforce training methods descended from Seneca and Evansville and Pittsburgh. The connections aren't always visible, but they're real. The ungainly LST, the large, slow target that crew members mocked and strategists desperately needed, represents the moment when American manufacturing fully committed to modern mass production of complex systems. The moment when speed of production became as important as quality of product. The moment when good enough, in sufficient quantity, delivered on time, defeated perfect, in insufficient quantity, delivered late. John Niedermair sketched an awkward ship in November 1941. By August 1945, that sketch had become 1,051 ships that changed warfare fundamentally. The transformation took less than 4 years. It required embracing welding despite traditionalist opposition. Building shipyards in cornfields, despite seeming absurdity. Training thousands of workers in weeks despite union objections. Accepting risks despite occasional catastrophic failures. Making trade-offs despite uncomfortable mathematics. But when Winston Churchill complained about destinies tied to goddamned LSTs, he was watching those ships make possible the liberation of Europe. The awkward, ungainly, rapidly built welded ships that carried democracy back to occupied shores, that carried tanks to beaches, that carried wounded men home, that carried the industrial might of American manufacturing into combat. That's their legacy. That's why the welding revolution mattered, not for elegance, not for perfection, for sufficiency, for quantity, for speed, for winning. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.